All right, let's do this curve sketching example here with a rational function. This one's going to be a little more interesting. So we're going to go through the same steps with all these. We're going to find the domain. We're going to find all our x and y intercepts. Those help nail down the graph, find any asymptotes, vertical or horizontal. That helps us find our end behavior, what happens on the left and right hand ends of our graphs. We find all our critical values by finding places where the derivative is 0 or undefined. We do a sign chart for the derivative. That'll give us where the function's increasing and decreasing and help us find our local extrema, local maxes and mins. We find our second derivative, use that in a sign chart to find our concavity, where we're concave up and concave down, and our inflection points, and we put that all together on a graph. Same steps every time. Okay, this guy has domain issues. So remember, you're never allowed to divide by 0. Our domain here, the bottom, x cubed, is not allowed to be 0, which implies x cannot be 0. So that means my domain is all real numbers except 0. So when I go to graph, I'm going to have two separate sections of graph that are not touching each other. That's why it's important to find our domain first. That also tells me I'm probably going to have a critical value at 0. Any place where the function's not even defined, the derivative's not going to be defined. I'm going to have a discontinuity in the derivative at 0. That needs to go on the sign chart. A lot of mistakes happen there. Okay, what about asymptotes? We're going to have to remember some information from college algebra and pre-calculus. Vertical asymptotes happen when the denominator equals 0. Wait, that's the work we just did. In most cases, finding your vertical asymptotes, finding the domain, is kind of the same math. We just write the answer differently. X cubed equals 0 implies x is 0. We have a vertical asymptote at x equals 0. Vertical asymptotes are vertical lines. They're not numbers. Our vertical asymptote here is x equals 0. Okay, what about horizontal asymptotes? Here we're looking for the limit as x approaches infinity of f of x, and limit as x approaches negative infinity of f of x. We want our infinite limits, our limits at infinity. And here, you remember, it's a rational function. We just look at the degrees of the top and bottom. We got to remember all those three different cases. If the top's bigger, you have no horizontal asymptote. If they're the same, you take the ratio of leading coefficients. If the bottom's bigger, the answer is 0. Both of these are 0. Take the limit as x goes to infinity. This thing goes to 0. So that means our horizontal asymptote is the horizontal line y equals 0. Okay, so when I find stuff, I like to go ahead and put it on the graph. I'm going to give us plenty of space here, so we might end up with some extra white space here in this document. But I want to make sure I got plenty of room to do all my work. So I'm going to have a horizontal asymptote here, y equals 0. I like to dot that in. And a vertical asymptote at x equals 0. All right, let's find our intercepts. X-intercepts might have more than one. How do you always find x-intercepts? Always, in every situation ever, always set y equal to 0. So we're going to solve 0 equals, all bars in my way here, 7x squared minus 7 over x cubed. Now, a little shortcut we can use here, a trick. The only way a fraction can equal 0 is if the top equals 0. So set the top equal to 0. That's a quadratic. We could factor. We could use completing the square. Oh, it's already complete. Use quadratic form, or we could use the square root property. Move that 7 over. Divide both sides by 7. X squared equals 1. We get x is plus or minus 1. Take square root of both sides. Don't forget the plus or minus. Now remember, intercepts are points, not numbers. So my x-intercepts are the points 1, 0, negative 1, 0. Intercepts are points, not numbers. What about our y-intercept? How do we always, in every single situation for the rest of your life, how do you always find the y-intercept? You set x equal to 0. Always, or whatever your variable is. Oh, we can't. 0 is not in the domain. Look, I'm not allowed to, I would get negative 7 over 0. It's not in the domain. I can't. You know what that means? We have no y-intercept. That's okay. Sometimes you don't have one. All right, let's put what we just found on the graph, 1, 0 and negative 1, 0. Notice that we're crossing over our horizontal asymptote. That happens. On occasion, you will cross over a horizontal asymptote. Horizontal asymptotes only tell you what happens out here on the ends. They don't tell you anything about the middle. Anything can happen in the middle. Vertical asymptotes, though, you will never, ever cross. You cannot touch a vertical asymptote. They're like Star Trek force fields. The graph is going to come in and get closer and closer to this, but never touch it. So the graph is either going to come up like this, or it's going to come down like this and get closer. And same thing back here. The graph is either going to be coming in from positive infinity or from negative infinity and cross over that point. And the derivative is going to tell us all that. Okay, now let's find our critical values. These are places where the derivative equals 0 or does not exist. We already know we're going to have one place right there, 0. If the function's not even defined there, there's no way the derivative is going to exist there. All right, let's take the derivative. I'm just going to rewrite the function here so I have it in front of me. That's the original. Our derivative. I have to use quotient rule here. So derivative of the top times the bottom minus derivative of the bottom times leave the top alone all over the bottom squared. X cubed squared would be x to the 6th. All right, now we got to clean this up a little bit. So remember, all semester I've been telling you when you use quotient rule, and usually it's okay just to leave some nasty mess like this. Now we got to do something with it. So now we're going to have to do a little simplifying. So what do we get? We get 14x to the 4th minus 21 x to the 4th plus 21x squared over x to the 6th. Okay, I'm going to factor, let's combine like terms here. I think we get negative 7 x to the 4th plus 21x squared over x to the 6th. And I'm going to factor a negative 7x squared out of the top. And what will be left with? X squared minus 3. Definitely check my arithmetic there, but I think that's right. Now, you might be tempted to cancel out these x's here. You want to be careful doing that. because you don't want to lose any excluded values. Here, it wouldn't make any difference. We'd still have x to the fourth in the bottom. We still get an excluded value of 0. You're not allowed to plug 0 into this because you would get 0 in the denominator. You're not allowed to have 0 in the denominator. So here, let's just write that out. F prime of 0 does not exist. Can't plug 0 in because you can't have 0 in the bottom. Okay, where does f prime equal 0? Remember, a shortcut. The only way a fraction equals 0 is if the top equals 0. Okay, so how can the top equal 0? Well, x could be 0, but we've already said we're not allowed to use that. So that means this must be 0. Or x equals plus or minus the square root of 3. So we've got three critical values here. Let's list those out. We've got negative root 3, 0, and positive root 3. That guy's not going to give us a critical point because it's not a point on the graph, but we still have to include it in our sign chart. A lot of mistakes happen here. Places where the derivative doesn't exist still go in our sign chart. All right, so now let's do a sign chart for the derivative. So I'm going to, on here, list out all my critical values. Negative root 3, 0, and root 3. So notice I have 3 regions here. I've got this region here, negative infinity to negative root 3. Oh, I've got a lot more than 3. I've got 1, 2, 3, 4 regions. This region is negative root 3 up to 0. This region is 0 up to square root of 3. And then this final region is root 3 to infinity. I've got 4 different regions. I got to find the sign, plus or minus, of the derivative in each one of these regions. So just for simplicity, I'm going to rewrite our derivative right here. Now, this is so much easier when you're doing sign charts to use all of your factors. So I'm going to rewrite my number line here, and I'm going to list out all my factors along the side. So this is a factor right there, negative 7x squared. This is a factor, x squared minus 3. And that's a factor, x to the 6th. If I figure out where these guys are positive or negative, in what regions, it makes doing this sign chart a lot easier. We could absolutely just take these test points I'm going to pick out and just plug them into the whole thing, see if we get a positive or negative. And maybe I'll do one just to show you. But it's easier if we do these one factor at a time. So let's pick any number that lives back here. Maybe we'll test x equals negative 4. I know that lives in this region. This thing is always negative. I don't care what number you plug in there. X squared is positive times negative 7. That guy's negative. In fact, he's going to be negative everywhere, no matter what value you plug in. What about this guy here? Negative 4 squared would be positive 16 minus 3. That's a positive. X to the 6th power, that's always positive. Doesn't matter what you plug in. If you take something to an even power, it's always, and in fact, I can go ahead and fill that in everywhere. It's always positive. So this guy really is going to determine where we switch over. Okay, let's plug in a value in this region. So negative 1. would be a good test value there. -1 squared is +1 minus 3 is negative. Pick a test value over here, maybe 1. 1 squared minus 3 is still negative. Pick a test value over here, maybe 4. Anything that's, I could pick 100. 4 squared, 16 minus 3, it's a positive. I don't care what the number is. I just care positive or negative. Now look, going down. An even number of negatives is negative, an odd number is positive. I've only got one negative. I got negative times a positive times a positive. That whole thing is negative. Here, I've got 2 negatives. Negative times a negative. This guy's not going to, I could have ignored him. He doesn't change anything. Only the negatives matter. 2 negatives makes a positive. Here, 2 negatives, still positive. Only one, oops, only one negative is negative. Now, again, we didn't have to break this up into factors. I could have just plugged, say for this region right here, plug 1 into the whole thing. So I could have, I'm going to erase this, but I could have done f prime of 1 is -7 times 1 times 1 minus 3 over 1. That's -2 times -7. I get +14. It's positive. So look, in this region, because I picked one value in this region, that's all you got to pick, I got a positive number. You pick one value in each region of your number line and plug it into the derivative, see if you get a positive or a negative answer. That's all you care about. It's easier if you use factors because you can do the plugging in your head. All right, now let's look at what these mean. My graph is going down here. We're decreasing because I have a negative derivative, and we're increasing here. That makes me think I have a local min right there. On this region, we're still increasing. So we know we have a vertical asymptote here. So recall vertical asymptote at x equals 0. So the graph is going to be increasing on the left of that and increasing on the right again. And then over here, we're decreasing again. Negative derivative means the original function is decreasing. So look, he's going up and then back down. The graph's going to do something like this. That means we've got a local max right here. Okay, let's write all this out. So f, the original, is increasing on this interval from -√3 up to 0. But then it's going to start over. You can't just go from here to here. You can't say you're increasing the whole time because it starts over. Like we have to do one little region at a time. We were increasing here and then again here. So union 0 to √3. F is decreasing on which intervals? This interval here, -∞ to -√3, and then again, √3 to infinity. We said we had a local min at x equals -√3 of, now we got to plug that value back into the original. Mistakes happen here all the time. Because we're working with the derivative right now. Like everything I've done for the last 5 minutes has been about the derivative. It's very common for people to take this value and just plug it in here. I already know what I get there. I get 0. That's why it was a critical value. No, you got to go back to the original. So I'm going to rewrite our function here. That would be 7 negative root 3 squared minus 7 over negative root 3 cubed. Whatever that number is, it's going to be some nasty number. So squaring that number is going to make it positive. I'll get 7 root 3 minus, oh, I lied. Negative root 3 squared is just 3. And then negative root 3 cubed is going to be negative root 3 cubed. There's not much we can do with it. Like we could simplify the radical, but it doesn't really matter. Okay, so what do we get there? We get 21 minus 7. We get 14 over negative root 3 cubed. So maybe we'll write that as negative 14 over 3 to the 3/2 power. I could rationalize the denominator, but it's not going to make it much prettier. We're just going to leave it like that. That was a local min. So that's the point. We always want to write these as points. Okay, then we have a local max at x equals positive root 3. So we got to plug this into the original of f of root 3 would be 7 root 3 squared minus 7 over root 3 cubed. Then we're going to get the same thing. We're going to get the same thing, only it's going to be the positive version of that. Oh, I wrote that upside down. My power on 3 here is 3/2. So this is my local max. That was root 3, 14 over 3 to the 3/2 power. All right, let's put those on the graph. So negative root 3, that's a little more than negative 1. And we had a negative value here. So we're just kind of estimating here. That was the point, negative root 3, negative 14 over 3 to the 3/2 power. And then over here, we have the positive version of that. Root 3 is like 1.7-ish. So we want to go like almost to 2, kind of. Here's negative 2. That would be root 3 positive 14 over 3 to the 3/2 power. Okay, so we're going to have a local min there. Our graph is going to do something like this. And then our graph, we know we're increasing and I kind of already know what the graph's going to do. I'm crossing over my horizontal asymptote here. If I'm looking backwards, and I'm going to be going back and approaching this asymptote. And then over here, I know I'm going to come up, hit that maximum, and then decrease back down. Now I know I can't shoot down like this because there's no more intercept. There's no intercept over here. So I know the graph can't shoot down. And I already said this is an asymptote. I know the graph's going to come in like this. So just using college algebra information, we could finish the graph, but let's find our concavity. So we're increasing from negative 3, root 3. That's supposed to be a root 3. I apologize. We're increasing from negative root 3 up to 0. So from here to here, we're increasing, and we said that's a vertical asymptote. So the graph has to look like that. It has to. Because this region right here, we were increasing. Negative root 3 up to 0. And then where else were we increasing? 0 to root 3. So this one's tricky. I'm increasing from 0 up to root 3, from here to here. Remember, we're looking at x values. The only way that can happen is if the graph comes up from negative infinity. I kind of missed there. Comes up from negative infinity and gets to that point. So if we're going backwards, that's kind of a sloppy drawing, but you see what I'm going for there. That's our vertical asymptote, and we're approaching that as we go down. Okay, then our graph is decreasing on the other two regions, from negative infinity to negative root 3, and then again from root 3 to positive infinity. So decreasing. Now remember, we've got an asymptote here. I'm not decreasing like this. I'm not crossing over. There's no x-intercept here. If there were, I would have found it. The graph cannot do that. I know there's no x-intercept there because I found the only two x-intercepts. The graph is coming in like this from that asymptote. And similarly over here, I say this thing is decreasing. It can't do that. There's no intercept there. It has to do this. That's an asymptote. So that the region where we're decreasing was negative infinity to negative root 3. That's decreasing. And then decreasing again over here, root 3 to infinity. Look, the graph's going down. So I'm almost done. All I got to do now is see if I have any inflection points and maybe clean up a little bit with my concavity. Do I want a right side up bowl or an upside down bowl? So now we're going to do our second derivative. For concavity, we find the second derivative. Okay, so let's rewrite our first derivative. It was, I'm going to leave it in its unfactored form right there, that guy. Negative 7x to the 4th. I don't remember what it was. Plus 21x squared over x to the 6th. Okay, let's take his derivative. The second derivative is the derivative of the derivative. So I got to use quotient rule here. Derivative of the top, negative 28x cubed plus, what's that, 42x times the bottom, leave the bottom alone, minus derivative of the bottom, 5x to the 6th, times leave the top alone. Negative 7x to the 4th plus 21x squared, all over the bottom squared. That'll be x to the 12th. And we're going to have to do the algebra here. Now, maybe we could make this a little easier because I do have a common factor of x to the 6th there. So maybe I could factor that out first. Sometimes there are little tricks you want to look for. So if I factor out that x to the 6th first, I'll have negative 28x cubed plus 42x. Now I didn't factor out the 5, so I'm going to do two steps at once here. I'm going to distribute that negative 5, but I've pulled out the x to the 6th. So that'll be plus 35x to the 4th minus, what is that, 105 x squared. And as I'm writing this, I'm realizing something's not right. We should not be getting all those powers. I done goofed. I'm not going to restart this whole thing over. I just goofed right there. And I hope you guys caught me as I was doing it. Derivative of the top, leave the bottom alone. Minus derivative of the bottom, this should be 6x to the 5th derivative of the bottom is 6x to the 5th times leave the top alone. Okay, we're going to get prettier stuff now. So I apologize for that. Factor out an x to the 5th here. So I've got, I got to be careful here. I'm going to rewrite it. I'm going to rewrite it and do this in 2 steps. I'm going to have an x left there and a -6 left here that I have to distribute. I got to be careful with my parentheses here. Okay, so I pulled out an x to the 5th, leaving an x behind there and a 6 there. So the x to the 5th is going to come along for the ride, distributing this x here, -28x to the 4th plus 42x squared. And now I'm going to distribute that 6. I get a plus another 42. And this one's x to the 4th. And then 6 times 21, I think that's 126. That would be 120 plus 6, 126 x squared, and that's going to be negative. And that's all over x to the 12th. Okay, anything pretty happen here? So I've got these 2 common factors. In fact, I've got a bunch more x's I could pull out here. I'll do that in a minute. But I've got 42 minus 28 is that 14? X to the 4th. And then I'm going to need my calculator here. 42 minus 126. -84 x squared. All right, let's check all of my math here. So this guy and that guy were common factor or common terms, like terms. 42 minus 28 should be 14. And then these guys were like terms. Now I could pull another x squared out of there. That's going to make simplifying this a little easier. So pulling an x squared out, I'll get x to the 7th outside. 14x squared minus 84 all over x to the 12th. And again, you might be tempted to cancel, and in this case, it wouldn't hurt because I still have x's in the denominator. If I want to cancel these, like I'll go ahead and write it just to show you it's not going to hurt anything in this case. That would be x to the 5th in the bottom. But you do want to be careful because anytime you cancel, you got to make sure that whatever you're canceling is still not in your domain. Like that's still a bad guy. 0 is still not allowed. Okay, so possible inflection points possible points of inflection, POIs, are when the second derivative equals 0. That's when the top equals 0. But when I do my number line, I need to include every place the second derivative either equals 0 or does not exist. So let's set the top equal to 0. And we'll get x squared is 84 over 14. Does that go in evenly? Oh, it does. Look at that. We're getting plus or minus square root of 6. All right, so those are my possible points of inflection that will occur at those values. But when I do my number line, I also remember the second derivative is not defined at 0. So let's write that down. F double prime of 0 does not exist. All right. So now I'm gonna pause. Okay, so I've come down below my graph because I ran out of space up there. Here's my second derivative. I'm going to do a sign chart for the second derivative. This will give me concavity. So I'm going to include on here any place where the second derivative equaled 0, that was negative root 6 and positive root 6, and any place where it doesn't exist, 0. So I've got 4 different regions here. And I have to find the sign, plus or minus, of the second derivative in each of those. So I think it would be easier to factor out that 14 and just look at the factors. Now, again, there's nothing wrong with this. You pick a test value from each region and you plug it into this function, you get an answer, write down whether it's positive or negative. Perfectly fine way to do it. I'm going to take what I think is a shortcut that I think is a lot easier. I'm going to write down my factors here, x squared minus 6 and x to the 5th. 14 is always positive. It's not going to change anything. So I've got these regions. Don't forget to do this region. Sometimes I write things a little too big, and when we all do this, we forget to do this region back here. Okay, let's plug in any value from back here. So root 6, I don't know, it's less than 10. I'm going to plug in 10, negative 10. That's 100 minus 6, 94. That's a positive. A negative to the 5th power is a negative. A negative times a positive is a negative. We plug in anything into this region. I'm going to use, I don't know, negative 1. These are my test points here. Negative 1 squared is 1 minus 6, negative 5. It's a negative. Negative 1 to an odd power is a negative. 2 negatives makes a positive. Plug in any test point over here. I'm going to plug in 1. 1 minus 6 is negative. 1 to the 5th power is positive. A negative times a positive is a negative. And then I'll plug in any value of, it doesn't matter, anything bigger than root 6. I'll plug in 10. It's 100 minus 6, I get a positive. I don't care what the number is, it's positive. 10 to the 5th power, it's a positive number. 2 positives makes a positive. Again, if you want to use this, plug 10 into the whole thing, get your calculator out, plug 10 into the whole thing, you'll get a positive number. All right, so any place where we're negative is concave down. Any place where we're positive is concave up. Where we switch from one to the other, as long as we're in the domain, is a point of inflection. So look, we're swapping right there. I've got myself a point of inflection, a POI right there. And I've got one right here, a POI, a inflection point, a point of inflection. This guy's not a point of inflection because that's not a point on the graph. That's my vertical asymptote. Okay, so let's write down what we have right now. We're concave up. I'll write that one first. On these 2 regions in here, that was negative root 6 up to 0. I'll write all these out. This was negative infinity to root 6. This was 0 to root 6, that region. And this was root 6 to infinity. So where were we up? Negative root 6 to 0, union, positive root 6 to infinity. We were concave down, negative infinity to negative root 6. And then again, I lied. I apologize. Hopefully you guys caught that. I was doing up. This was the next up, not that. 0 to root 6. Up and what have I done? Oh, I lied here. It's not that my numbers were wrong. Is that I lied here. I lied a while ago. Negative. Some people are probably confused. I apologize. Negative is down. Positive is up. Okay, so where were we up? The second derivative was positive in this region and in this region. Exactly what I wrote before. I just wrote the word wrong. And down, negative infinity to negative root 6. And then again, 0 to root 6. We have points of inflection at negative root 6. I got to plug that into the original. That's where that's at. When somebody says, where does it occur? That's where. Of, now we plug this in the original. So we're going to plug it back here. And that would be 7 times negative root 6 squared minus 7 over negative root 6 cubed. All right, negative root 6 squared would be positive 6 times 7. So that's 42 minus 7. And I would write this as negative 6 to the 3/2 power. What's 42 minus 7? That's 35. So this will be negative 35 over 6 to the 3/2 power. I just moved the negative to the top. So that's 1 point of inflection. And let's circle this stuff. And then the other one, we're going to get basically the same thing. Positive root 6, plug that into the original function. I'm going to get the same thing on top. I get 35, and on the bottom, I just get a positive number, 6 to the 3/2 power. So that would be positive root 6. Oops. 35 over 6 to the 3/2 power. 2 points of inflection. Let's put those on the graph. Okay, negative root 6. Let's get our calculator out just to get an idea how big that is. Square root of 6. It's like 2.5-ish. So it's going to be about here, and same on the other side. So that was negative root 6, negative 35 over 6 to the 3/2 power. So that's where I switch from concave down to concave up. So I kind of want to try to draw that on the graph. See, this part looks like an upside down bowl. This part looks like a right side up bowl. And then same thing over here. See, we can kind of already see it. Look, it looks like an upside down bowl right there, concave down. And then this part looks concave up. From here on, kind of looks like I'm trying to draw this. Now, remember that I see this happen a lot. When we say concave up does not mean it has to complete the bowl. It doesn't have to go down and come back up. This is still concave down, something going like that. That's the half of a right side up bowl. That's still concave up. It does not have to go boo and bounce back up. So from this point, which I'm going to label root 6 positive 35 over 6 to the 3/2 power. From here on, we are concave up. And for this whole region here, we are concave down. I'm trying to trace over all of that. This is all down. From here on, it looks more like, woo. Now, it's not going to bounce up. I don't want to give the wrong impression. It's not going woo and back up. Concave down goes ooh like that. Concave up goes ooh like that. This is up. This is down. And that's what I'm trying to draw, something that looks like that. All right. So this was a long, hard, nasty one. They can get a little bit worse than this when you have radicals. But this is like, this was a bad one. This would be like a level 8 problem here. And that's a good place to stop.